Hello, you're welcome. All right, so now we are going to be looking at change of states, okay, in which we will describe in details latent heat. Okay, so now what is actually latent heat? Now, latent heat, if you go by dictionary definition, okay, is simply hidden heat. Now, in physics, latent heat is heat that is actually required to change the state of a substance, right? So it is the heat change in state heat energy required to change the state of a substance. All right, and of course, you know that when we are talking about the change in state, okay, we are basically looking at a change in state that require you to convert solid, okay, to liquid. So this is a change in state, which of course we call this melting, right? We call this melting. All right, then we'll now move from liquid to gas, okay, which of course we call vaporization or boiling, right? So this state actually is boiling, and it happened at boiling point. All right, so now let's get to the business. Okay, so now change in state, okay. Let me actually illustrate using a very simple, right, substance, which of course is ice, right? When you heat ice, it actually heat ice changes to liquid water, right? Then when you heat water to boiling point, it changes to steam. Okay, so we know this actually occur at a particular temperature, which for ice we know it is at 0 degrees Celsius, and we know this occur at a particular temperature. Okay, for water we also know that this happen at 100 degrees Celsius. All right, so now there's always the energy that is actually supplied for this change in state, okay, is hidden. Why is it called hidden? Why? Because it doesn't show itself in any rise in temperature. Now, how will I illustrate that? I will illustrate that using a graph, okay, the graph of change in state. Now let's say I want to draw a graph of change in state where, okay, I will draw the heat supplied to a body against heat supplied, okay, and against temperature. Okay, now temperature is in the horizontal. We use temperature is the horizontal axis, right? And of course heat, all right, so that's the vertical axis. Okay, so now of course you know very well, if I'm actually looking at the temperature of ice is below zero. Okay, this origin is below 0 degree. Okay, ice is still ice when the temperature is below 0 degrees Celsius. So let's say I have minus theta degrees Celsius. Okay, theta degrees Celsius. At this point, ice is still solid. All right, ice start melting at 0 degrees Celsius. Now, when I hit the temperature of ice at this particular negative, okay, temperature, now that ice is not gonna melt at this temperature. It only melt at 0 degrees Celsius. So which simply means that the first thing that will happen is that the temperature of the ice will first rise. Okay, you keep on rising. This shows rise in temperature to the point where, okay, it gets to 0 degrees Celsius, right? The origin is 0 degrees Celsius. Now at 0 degrees Celsius, this ice, okay, is going to melt at 0 degrees Celsius. So probably I'm expecting the temperature to keep on rising even as the gas is melting. But it happened that at this particular point, at 0 degrees Celsius, where this ice start melting, temperature stop rising. The temperature, okay, is discovered to stop rising. But that at this point now, I'm gonna draw a horizontal line showing that at 0 degrees Celsius, even when I keep on supplying the heat, the temperature is constant. All right. So let's say the heat actually supplies, let's say the very first heat that supplied that moves the temperature from this to this point, let me call this H1, right? Then the temperature move from the heat has supplied the heat from H1 to H2, and the temperature still remain horizontal, it's not increasing. So between these points, okay, of course at 0 degrees Celsius, that's at the origin, okay, H1 to H2, where heat is being supplied and the temperature remain constant. What you have here, right, is what is regarded as latent heat. This heat from H1 to H2 is latent heat. Why? Because even when the heat is being supplied, okay, increase from H1 to H2, all right, the temperature still remain constant. Normally, one indicator of heat is the fact that once you supply heat to a body, the temperature rises, all right? So in this case, the heat is being supplied, but the temperature is not rising. Okay, it remains constant. So that's what we call such heat hidden heat. So it's a heat that doesn't show itself in a rise in temperature. Okay, and this actually occurs, this latent heat occurs all through the period of the melting. So this region is a region that occur during melting. Okay, so this is at this point, this is where you have what is known as the melting point. Please pardon me, the melting point. So melting point. So now let me illustrate, okay, further. So which simply means that if I need to melt any substance, the very first thing I'm going to do is I have to raise the temperature first to the melting point. Okay, in this case now we have ice. So the first thing I did was to raise this temperature of ice to melting point. So I have to supply energy, okay? So the heat energy I supply to raise the temperature to melting ice is actually in terms of the heat capacity, okay? Then after supplying the heat to raise the temperature of that body to melting point, then you now have to melt that particular substance, okay? In the case of ice, okay, I raise the temperature of ice to 0 degrees Celsius, okay, first. So when the ice actually reaches 0 degrees Celsius, then I start the melting. So the melting starts at this point. So energy moves from 0 to H1, from H1 to H2. So please take note of that, and of course I will illustrate that. I'll still illustrate that. Okay, so after the ice must have finished melting, then I now notice that the temperature start rising again. Okay, so temperature start rising again. So it will rise to a point where I notice another steady temperature. Okay, and of course, since I'm illustrating with ice, the point where this temperature, okay, becomes steady again now is another point. Okay, means, of course, you know very well that is the point known as the boiling point, and we know that water boil at 100 degrees Celsius, right? So at that point now you discover that I will now have temperature at this point now becoming, excuse me, is becoming very steady again. All right, so this is the point now that I call the boiling point. So as it's discovered at our boiling point again, temperature become constant even when the energy is being supplied. Okay, so let me actually let's stress that to the temperature as to the heat as is. Okay, let's say the heat that is actually supplied at that particular time is now have H3, okay? Then throughout, so please, the horizontal axis is the heat axis, okay? Please pardon me. The vertical axis is temperature, so I made a mistake. So it's always temperature against heat. So I'm using the vertical axis is temperature, okay? While horizontal axis is heat. So quantity of heat. So now this temperature, okay, so keep on increasing. This the heat increases from H3, okay, to probably H4, while the temperature still remain steady throughout that period. All right, and we also know that such heat is also known as latent heat. All right, so there's another latent heat I have here. So we simply mean that for ice, okay, there are two latent heat. One latent heat is supplied during melting, and of course the second latent heat is supplied during boiling, okay? Then I think after the whole substance, the whole water has actually boiled, then of course the temperature start, okay? So now this is just change of, this actually is change of state diagram. So please take note. Now my emphasis is the point where the change of state occur at melting point and at boiling point. So the heat that is actually supplied at that point is known as latent heat. All right, so our emphasis is on latent heat. All right, so now let's now go to the tutorial proper. So now if you are not being asked to define latent heat, okay, from physics perspective, so how will I define latent heat? Okay, now I will define latent heat as a quantity of heat energy. Right, quantity of heat. Quantity of heat required to change the state of matter. All right, then without any change in temperature, without any change in temperature. All right, so what simply means that even though latent heat is being supplied to change the state of a substance, okay, but you won't see any change in temperature. There is no noticeable change in temperature, and that is why it is being called latent heat. Okay, so that means now by formula I can simply say, okay, let's say QB, let Q be the quantity of latent heat, okay, supplied. So of course we know that the quantity of heat energy, okay, supplied is always given as mass multiplied by C multiplied by change in temperature. But in terms of latent heat, okay, what I have is quantity of heat energy is equal to mass then multiplied by L. So now there's no change in temperature, remember, at latent heat. So now quantity of heat energy is equal to mass times L. Now this L is a constant, right? Which of course we know that is a constant called specific, but this time around it is specific latent heat. Specific latent heat. So now the latent heat, okay, is of two types. Let's say types of latent heat. Depending on the latent heat we're actually looking at, right? We have two types of latent heat. All right, now latent heat can either be, okay, latent heat of fusion, okay, then of course, okay, now of course, let me, I want to state in terms of specific, okay, so types of specific latent heat, let's just, since that is going to be types of specific, okay, types of specific latent heat. All right, so we have specific latent heat can either be specific latent heat, specific latent heat of fusion, or it can be the specific latent heat, latent heat of vaporization. Okay, all right, okay, latent heat. So it's either it is specific latent heat of fusion and it is specific latent heat of vaporization. Okay, so now of course you know that for specific latent heat of fusion is the occurs during melting. All right, this is the one that occurs during melting. That of vaporization occurs during boiling. All right, so now how do I define it? Now before I define it, of course, remember the L here, we just get that from let me bring the formula again, right? Which we know that the quantity of heat energy supplied during melting or boiling, okay? The quantity of latent heat supply is equal to mass multiplied by the specific latent heat, all right? So which simply means that if I should make the specific latent heat the subject of formula, that's going to be quantity of heat supplied, then divided by mass, okay? So SI unit of quantity that is of heat is joule, SI unit of mass is kilogram. All right, so it simply means that specific latent heat, all right, is joule per kilogram. Okay, so now this specific latent heat, if I use the symbol LF, I am actually talking about the specific latent heat of fusion. That's LF. If the symbol is LV, okay, of course it still holds the same formula. Quantity of heat supply, okay, I'm actually referring to specific latent heat of vaporization. So now how do I define specific latent heat? Now specific latent heat is defined as the quantity of heat energy required to change, okay, let me define that of fusion, okay, please pardon me. Okay, so how do I define specific latent heat of fusion? All right, now specific latent heat of fusion, LF, is defined as the quantity of heat energy that is required to change 1 kilogram. Remember, it is specific. When we are defining it in terms of being specific, I have to specify the mass, okay? So specific latent heat of fusion is the quantity of heat energy that is required to change 1 kilogram of a substance from its liquid state. From its please pardon me, fusion is from solid state, okay, from its solid state to liquid state. So that is what's, let me repeat again, the specific latent heat of fusion is the quantity of heat energy that is required to change 1 kilogram of a substance from its solid state to its liquid state without any change in temperature. I have to include without any change in temperature, because when it has to do with latent heat, there's no change in temperature, okay? So now If I want to define it in terms of specific latent heat of vaporization, okay, it's still the same way, right? So this okay is for, so I'll define it the same way. So I will simply say that specific latent heat of vaporization is the quantity of heat energy required to change 1 kilogram of a substance from this time around its liquid state to gaseous state. From its liquid state to gaseous state. So that actually gives us two latent heats. Okay, specific latent heat. We have specific latent heat of fusion, all right, and we have specific latent heat of vaporization, depending on what you're looking for. Okay, in either case, specific latent heat or the quantity of heat energy supply, okay, to change state is always given as mass, okay, multiplied by the specific latent heat. Now, just a quick reminder, in case you're being asked to evaluate the total energy, all right, total energy, okay, that is required to actually change the state of a substance from a, okay, now that total energy may not necessarily be the latent heat. Remember, latent heat actually occur at the temperature, okay, the temperature, the change of state temperature, if you understand what I mean. Let's say I have ice, and this ice is possibly at -4 degrees Celsius, and I want to melt this ice, okay, and of course I want to melt this ice completely to water, and that, all right, actually occurs at the temperature of 0 degrees Celsius. So if I want to get the total energy that is required for this to happen, the total energy that's required to this to happen is not the energy that's required to melt the water, which of course is MLF, right? Mass times specific latent heat. Because the truth of the matter, okay, this latent heat, okay, this latent heat only occur at 0 degrees Celsius, right? When the ice is already at 0 degrees Celsius, that is where you apply this. But the question is, what happens to the heat that I supply? Because first I need to actually raise the temperature of the ice from 4 degrees Celsius till it get to 0 degrees Celsius. So that heat is also part of it. All right. I'm only gonna use just this latent heat if I was asked to, okay, find the energy required to melt ice that is already at 0 degrees Celsius. Okay, so I can just use this because the ice is already at 0 degrees Celsius. But if this ice is not at 0 degrees Celsius, it's at a lower temperature, okay, I have to first raise the temperature. That is why when I draw the graph of change of state, remember first thing that actually happened in that graph. Okay, let me draw that again. The first thing that I did was to actually raise the temperature before the change of state actually kicks in, all right? Okay, so remember, the very first thing you have to do is to, okay, raise the temperature. So I have to raise the temperature before the latent heat actually kicks in, right? So this energy that's required to raise this temperature from here to here, all right, is different from the energy that is actually required to actually melt the ice completely. So let me now go to what so in this case now, the total energy, if you are being asked to find the total energy is going to be, first of all, the energy, all right? Let me write it in order. All right, first of all, the energy that's required to raise the temperature of this particular body to from -4 degrees Celsius to 0 degrees Celsius. So that energy, of course, the energy that's required to raise temperature is given as MC, change in temperature. All right, that's what we treated previously. Then after raising the temperature to 0 degrees Celsius, I need to melt that particular ice. So it is now you are gonna apply mlf. Okay, so this is the total energy that is actually required to handle this. Now just take note of this formula at by the time we apply it, okay, because we're going to be solving question in the next video. Okay, you will actually have a better understanding of it. Okay, so let's proceed. So what are we doing now? So we're going to look at how to determine specific latent heat. Okay, determination of specific latent heat. So as we already know, right, each substance, excuse me, every substance have their own specific heat capacity, the same way they also have specific latent heat. All right, depending on what you're looking at, is it fusion or vaporization? So we're looking at the determination of specific, all right, latent heat. Let me just call it SL, specific latent heat, SLH. Okay, so whether what you want to determine is the specific latent heat of fusion, or you are looking at the determination of specific latent heat of vaporization, both of them, all right, the method that is actually employed is two methods. Okay, as usual, is two methods, which of course the very first method is mixture, method of mixture, and of course we've actually talked about the second method is electrical method. Okay, so it's still the same principle, right? Let's say starting with that of mixture. All right, it's still the same principle with what we actually talked about when we discuss determination of specific heat capacity. All right, you know that for mixture method we employ the principle that, okay, heat lost, because that particular material I want to melt, I have to bring it in contact with a hot object so that heat will be transferred from the hot object to that material so that the heat it will melt. Okay, so the principle goes this way: heat lost by the hot object is equal to heat gain. All right, now, but in this case, okay, this object didn't just lose heat. Okay, the object that gains heat didn't just gain it for anything. Okay, so the heat lost by the hot object is equal to the latent heat. So let me put it this way: equal to the latent heat, all right, that is actually required to change the state of that particular object. So in this case now, let's say the object that's losing the heat, all right, let me say the temperature is MC, change in temperature. That object has a heat, okay, supplied to it, which I can measure by let me call it M1 C1, all right. Then of course change in temperature. So it is this heat energy of this hot substance, all right, that is now supplied to as a latent heat to the other substance to melt it. So of course latent heat is ML, right? So if it is fusion, it's MLF, and of course if it is vaporization, right, it's still the same principle. All you just need to do is LV. So this is the principle for mixture method. Heat loss is equal to the latent heat that is required to melt or to change the state of the substance. All right, of course we'll discuss how this work with example, but let's talk about electrical method. Okay, so electrical method. Okay, So in the case of electrical method, it's still the same principle, but the difference is that, all right, I will have to supply my energy from electrical heater. All right, so of course I've shown you how to evaluate electrical energy. Electrical energy given us electrical power multiplied by time. All right, it is now what is actually supplied to melt or to change the state, ml. Okay, so if we are dealing with electrical heat energy supplied to melt a substance, that's going to be mlf. All right, if it is electrical heat energy that is supplied to actually vaporize the substance or boil it, that's going to be mlv. So in either case, it's still the same principle. And of course, you know very well that the formula can, power times time, can also be given as IVT. I've given you all this, all right? It's still gonna be, all right? You can also write it in terms of current square multiplied by resistance times time. You can also write it in terms of V square, okay, multiplied by T all over R, still equal to mlf. Okay, so any of these can work. All right, now the one you choose to use depend on the question, what is given in the question. All right, so a question where what is given is of just power and the time for the supply of the heat, right, you use this. But if the questions involve temperature or current being indicated, voltage and time, you use. So just take your time, write down. All I just need you to, okay, understand the basis of, okay, the concept behind the entire topic, then get the key formula, write them down, understand how they are being derived, okay, understand their parameters, and we will definitely use them to solve typical examination question. And by the time we do that, okay, you have a better grasp of the entire topic. So do that. Click on the next video as we proceed. All right, see you in the next video. Thank you very much.